Containers have changed the way we deploy, run, and scale applications. But what are they exactly? How are they different from virtual machines? And why should you care about their security? Let's talk about containers. Before we continue, make sure to check out our newsletter. There's more details in the link in the description below. Containers are a way of solving an old problem when developing software. When developers say it works on my machine, but it doesn't really work in production. Containers are a way of shipping the developer's machine, dependencies and all. Large companies, like Netflix, use container orchestration as the underpinning infrastructure that powers their services. Running millions of containers allows tasks like batch processing, content analysis, and conversion to happen in controlled environments, with predictable and reproducible results every time. They are also considered a lighter form of virtualization, even if the technologies that power containers are not necessarily virtualizing anything, in the same way that virtual machines are. The comparisons with virtual machines is common, as the workloads are essentially isolated with both technologies, but the way to reach that isolation is different in each case. The key difference between containers and virtual machines lies in how they isolate that workload. Virtual machines emulate hardware, meaning that each VM will run with its own operating system on top of a hypervisor. This makes them comparatively resource-intensive but versatile. Containers, on the other hand, isolate processes using the host's operating system. They share the host's kernel, which makes them lightweight and much faster to spin up. Think of a VM as a full house, while a container is like an apartment. Both give you isolation, but containers are built for efficiency. Virtual machines are preferable when you have legacy applications, or just any piece of software not developed with containerization in mind. The change in mindset requires applications to be cleanly separated from the data layer, and should cleanly resist unexpected shutdowns and restarts, without corrupting the application or the data itself, which is something that, unless you're actively developing for, is very hard to achieve after the fact. Containers, on the other hand, are ideally suited for situations where you are able to have multiple or independent processing units that handle individual snippets of data, for example, serving web pages where each client is independent of others. Thus, virtual machines and containers are not necessarily a replacement for each other, but rather have complementary advantages that can and should be leveraged according to each use case. A one-size-fits-all approach for either is not optimal in every scenario. Under the hood, Linux containers rely on technologies like namespaces, which isolate resources like process IDs, network interfaces, and file systems, making each container feel like it's running on its own mini operating system. Then there's control groups, or C groups. These manage resource allocation, ensuring one container doesn't hog all the CPU or memory. And then, union file systems. These allow containers to use layers of their file system, which leads us to how to build containers. Containers are like cakes, built in layers. For example, if you're building a web server with Apache and PHP, you start with the base layer, like Ubuntu or Alpine Linux, then you add Apache as a layer, then you add another layer with PHP, and finally you add your application code. Each layer is read-only, except the top layer where changes can be made. This layered approach makes containers efficient and reduces duplication. Multiple containers can share the same layers. Here's the crucial point. The kernel inside the container is not separate. It's the same kernel as the host system. This is what makes containers lightweight, but it's also a potential risk. A vulnerability in the host kernel can be exploited from inside the container. From a security perspective, patching the host kernel is critical. Containers may provide isolation, but they are not foolproof. If the host kernel has a vulnerability, an attacker could potentially break out of the container, known as a container breakout, and gain access to the host system. We'll explain that next. A container breakout happens when an attacker exploits a vulnerability to escape the container's isolation. For instance, if a container is running a privileged process or the kernel isn't patched, it could allow an attacker to execute code on the host. This is why container security best practices, like limiting privileges and using tools like Security Enhanced Linux or AppArmor, are essential. Running an up-to-date kernel host, keeping up with container-related CVEs, and limiting the permissions and resources to the bare minimum needed for each container are all best practices to try and mitigate this risk. In traditional IT, servers were treated like pets. You cared for them individually. You gave them names and fixed them when they broke. In container world, servers are treated like cattle. They're interchangeable and disposable. If a container fails, you replace it with a new one. This mindset is a core principle of modern cloud-native applications. It's also a huge departure from previous practices in the area. To recap, containers are a powerful tool for process isolation, lightweight deployment, and scalability. But with this power comes responsibility, especially when it comes to patching the host and managing security. Whether you're building applications or managing infrastructure, understanding how containers work is essential in today's IT landscape. If you found this useful, hit the like button and subscribe for more Linux and IT insights. Thank you, and until the next one.